Six fundamental orbital elements completely define the spatial movement of any planet in the endless universe. The ecliptic plane serves as the primary base coordinate system for the precise calculation of celestial trajectories. Kepler's famous Transcendental equation allows for the flawless calculation of exact planetary positions years in advance. Modern celestial mechanics can efficiently calculate the orbits of new asteroids from just 3 observations.
Welcome. In this explainer, we're going to dive into the beautiful and, well, incredibly precise language of the universe. We're going to uncover the 6 key pieces of information, the orbital elements, that allow us to describe and, more importantly, predict the exact path of a planet through the sheer vastness of space. It really is the foundation of celestial mechanics, so let's get right into it.
So, here's our roadmap. We're going to break this down into 6 logical steps. First, we'll establish the orbital plane itself. Then, we'll sketch out the size and shape of the orbit on that plane. After that, we need to orient it correctly and lock it into a specific time. And once we have all that, we'll see how we can calculate a planet's exact position and, why this is so critical for astronomy.
All right, so to completely and unambiguously describe how a planet is moving, it turns out you need exactly 6 independent pieces of information. You can think of them as the coordinates of the cosmos. And together, we call them the orbital elements. And really, this question gets to the heart of the challenge in celestial mechanics. The solution, though, is just remarkably elegant. These 6 elements, when you put them all together, create a complete and totally unique fingerprint for any object's orbit around a central body, like our Sun. Okay, first things first. Before we can even think about drawing the shape of an orbit, we have to define the flat, 2-dimensional surface it lives on. You can't just draw a line in empty 3-dimensional space. You need a canvas. And this plane, well, this is our foundation. Every map needs a north, right? A starting point. For orbits, our fundamental reference is what we call the ecliptic plane. The easiest way to picture this is to imagine the giant, flat disk that's traced out by Earth's own orbit around the Sun. But just having a flat plane isn't enough. We need a direction, a 0-degree line. By convention, that line points from the Sun towards a fixed spot in the distant stars we call the vernal equinox. So our very first orbital element defines the tilt. It's called inclination, and we use the letter I for it. It's simply the angle between our planet's orbital plane and our reference ecliptic plane. So you can see, an inclination of 0 degrees would mean the planet is orbiting on the exact same floor as the Earth. And what's really cool is that this one number right off the bat tells you something huge about the orbit. If the inclination is between 0 and 90 degrees, that means the object is moving around the Sun in the same general direction as Earth and pretty much everything else in our solar system. We call that direct or prograde motion. But if that angle is greater than 90 degrees, it means it's going the wrong way. It's in a retrograde orbit.
Now for our second element, the longitude of the ascending node, or omega. This is what locks that tilted plane into a specific orientation. Just imagine those 2 planes, the ecliptic and the planet's orbit, intersecting. They cut through each other, creating a line. Now the point on that line where the planet crosses from below the ecliptic to above it, that's the ascending node. Omega is simply the angle measured along our reference ecliptic plane from the vernal equinox over to that ascending node.
All right, so with our plane now fixed in space by those first 2 elements, inclination and omega, we can finally move on to the next bit, defining the precise size and the precise shape of the elliptical path the planet travels within that plane. Our third element, the semi-major axis, which we call A, is really simple. It just defines the overall size of the orbit. It's half the length of the ellipse's longest dimension. But here's the crucial part. Thanks to Kepler's third law, this size is directly, unbreakably linked to the orbital period. The bigger the semi-major axis, the longer it takes for that planet to go around the Sun. Simple as that. So, if the semi-major axis gives us the size, how do we get the shape? Well, that's where our fourth element comes in. Eccentricity, or E. It's just a number that goes from 0 to almost 1. An eccentricity of 0 is a perfect circle. But as E creeps up toward 1, the orbit gets more and more stretched out. More squashed. Okay, let's take stock. We've defined our orbital plane, and we've drawn an ellipse with a specific size and shape on it. But we're not done. We still need to rotate that ellipse so it's pointing the right way, and then we have to start the clock for the planet's motion along that path. This orientation is handled by our 5th element, the argument of perihelion, or lowercase omega. Now this is an angle that's measured within the planet's own orbital plane. It starts at that ascending node we talked about and measures the angle around to the perihelion. That's the point in the orbit where the planet gets closest to the Sun. This step basically lets us grab our ellipse and rotate it into its correct alignment on the plane.
Our sixth and final element is a bit different from the rest. See, it's not about geometry, it's not about shape or orientation, it's about time. The time of perihelion passage, or T0, is the specific moment, the date and the time, that the planet was last at its closest point to the Sun. This is the absolute crucial anchor that connects this whole geometric structure to our calendar, to our clock.
So, with our full set of 6 elements now in hand, 2 for the plane, 2 for the shape of the ellipse, and 2 for its orientation and timing, we finally have everything we need to answer the ultimate question: where exactly is the planet at any given moment in time?
Now, the calculation itself is this fascinating 3-step process. The real problem is that planets don't move at a constant speed. They speed up when they get close to the Sun and slow way down when they're far away, so you can't just use a simple clock. Instead, we use a series of 3 different types of angles, what we call anomalies, to bridge the gap between the steady tick-tock of time and the planet's variable speed.
Step 1 involves a clever little trick. We calculate something called the mean anomaly, M. We basically imagine a fake planet, a ghost planet, moving in a perfect circle that takes the exact same amount of time to orbit as our real planet. Because its motion is perfectly uniform, it's super easy to calculate what angle it's moved through since it started. M is that angle. In essence, it's time, just expressed as an angle.
Next, we come to the absolute heart of the problem, the legendary Kepler's equation. This is what connects our simple, time-based mean anomaly, M, to a new angle called the eccentric anomaly, E, which is sort of a geometric go-between. Now look closely at that equation. The variable we want to find, E, appears both by itself and inside a sine function. That makes it what we call a transcendental equation, which is just a fancy way of saying there's no simple algebraic trick to solve for E. You just can't do it. We have to use numerical methods, basically successive approximations, to zero in on its value.
But once we've done the hard work and solved for that eccentric anomaly E, the final step is actually pretty straightforward. We can now just plug that value for E into these 2 formulas. The first one gives us the radius vector, r. That's the planet's actual real-time distance from the Sun. And the second one gives us the true anomaly, theta, its actual angular position along the orbit as seen from the Sun. And there you have it, the planet's position.
So this whole mathematical engine we've built, from the 6 elements all the way through to calculating the final position, is really what drives the 2 most powerful jobs of celestial mechanics. And you'll see these 2 tasks are basically mirror images of each other. On one hand, you have Ephemeris calculation. That's when we already know the 6 elements, and we use them to predict where an object will be at any time in the future or the past. The other side of the coin is orbit determination. That's when we spot something new, like a comet or an asteroid. We take 3 or more observations of its position, and we work backwards to figure out its unique 6 orbital elements.
So the single most important thing to take away from all this is that the system is completely deterministic. Once you know those 6 values, the inclination, the longitude of the ascending node, the semi-major axis, the eccentricity, the argument of perihelion, and the time of perihelion passage, you have captured the absolute essence of that orbit. Its path through space is completely, uniquely, and perfectly defined.
And that leads us to one final, really crucial point. This beautiful clockwork system we've just described, it's for an idealized 2-body problem, just 1 planet and 1 sun. But of course, our universe is filled with the gravitational tugs of other planets and moons and asteroids. And all these tiny little nudges, what we call perturbations, mean that over very long periods of time, these 6 constant elements, well, they actually change. Understanding how and why they evolve, that is the next great chapter in celestial mechanics.
Thank you, friends. Strive for understanding and become wiser. See you soon.